All right, in this T-Rex talk, we're going to be talking about an intro to thermal imaging, thermal cameras, thermal sights, different types of thermal optics. And this is going to be a very introductory talk. I don't have a huge amount of deep experience with thermal devices, but I do have a lot of wide experience with thermal devices, industrial ones, commercial ones, drone ones, several different things. But I feel like an introduction would be good because everybody on the internet is talking about thermal right now, and I blame Garand Thumb. In his urban survival video that I mentioned in the last podcast, he said this.
If you look at any of the conflicts going on right now, everybody's using thermal. If you don't have thermal, you're going to die to somebody who does use thermal.
Which is actually a really good thing. I'm really glad that that is happening, that it's getting the attention that it needs and deserves. And this is a really basic introduction to what it is, how it works, different types, etc. And one of the main things that I see on the internet is people arguing over terms, people saying thermal imagers are seeing in IR, and then other people say, no, that's what night vision does. And unfortunately, both sides are actually right. Now, as you know, visible light goes from about 400 nanometers to 700 nanometers. Those shorter wavelengths are your ultraviolet, indigo, blue, and then your longer wavelengths are your red. And then beyond that, you get your infrared. So your regular night vision, your image intensifier tubes are going to see up into about 1,000 nanometers of what they call near infrared. And those near infrared photons act a lot like visible photons. They act like light. They come from light sources and bounce off of stuff, just like regular light does. It's just light photons you can't see with your eye. And then there are longer waves of IR that most analog tubes cannot see. That's generally referred to as SWIR, shortwave infrared. That's like 1,000 nanometers to 3,000. I'll talk about that later. And then we get into far IR. It is far from the visible photons that you can see with your eye. And it now starts to act a lot less like light because it is now heat. This is somewhere, around 4,000 nanometers up to like 100,000 nanometers, which as a wavelength, that's actually 1 millimeter. So this is now heat. It no longer behaves quite the way that light does. And this infrared spectrum that goes from what our eyes can see all the way up to the top end of what heat is before it becomes microwaves, that is a really wide spectrum. That's like 10 times wider than the visible light that we actually can see. So there's a lot of information here. There's a lot of data that you can get if you can see into this much wider spectrum. And so these early thermal devices were very valuable, but they were also very complicated and expensive. Early thermal devices needed liquid nitrogen or something like that to keep the sensors cooled. They required a lot of power. They were obviously extremely expensive, but they did offer tremendous value for certain scientific applications and, of course, certain military applications. And today we are able to do a lot of thermal imaging with uncooled sensors. The sensor doesn't have to be kept at a precise temperature many degrees below zero in order to function. It can work at basically ambient temperatures. But it's still a pretty complicated camera mechanism because it requires the sensor itself to be made out of some fairly exotic materials that are not used for a whole lot of different things. And then even the lenses have to be pretty special. These longer wavelengths of light do not actually go through glass. So you have to make the lenses for these thermal cameras out of different substances like germanium, which is actually a real thing. Yeah, that adds a whole new layer of cost and complexity to the operation. Now, there have been some pretty affordable consumer thermal imaging devices. I know that most of you are probably familiar with the FLIR devices that were made a few years ago that plug straight into an iPhone or an Android. And that little dongle had two cameras on it. It had a thermal camera, and then it also had a visible camera because the thermal camera was ridiculously low resolution. I think it was like 30 pixels by 40 pixels, something like that. So 120 pixels overall. It could not show scenes with any detail whatsoever, and that's why they had the visible camera. The visible camera would kind of cheat. It would show you a sort of a grayscale image, and then they would superimpose the heat value on top of that image, and the giant blobs of heat data kind of showed you what the temperatures were of things, and then you could sort of see what's going on with a visible camera. So kind of janky, but for certain applications, that worked fine. If you're trying to figure out which burner of your stove is still warm, or you want to see the rough temperature of something that you can hold the camera on your phone up right next to, yeah, it's a very interesting thing to experiment with and explore with. But when it comes to longer range applications, more mission critical applications, you need considerably more resolution. And I think you also need a lot more sensitivity than those little FLIR devices could actually do. Now, FLIR makes a whole bunch of different kind of devices. There's commercial units for HVAC insulation, guys who install insulation and do different types of renovation work on houses obviously could benefit tremendously from having the ability to see thermal radiation and thermal reflectance and propagation, because then they can figure out what areas of a house are not properly insulated, for example. Then there's also industrial units that are really useful for things like firefighting. Obviously, when you are fighting a fire, you're inside of a structure, you're looking for where the heat sources actually are, and you're wanting to see through the tremendous amount of smoke that exists. And these longer wavelength heat photons, for lack of a better term, are able to pass through smoke that visible photons can't. So you're able to see through really thick, dense smoke in a way that visible light cannot. Even infrared light that you see with an image intensifier, regular night vision scope cannot. So there's tremendous capabilities that these things offer to different missions and let you get a whole lot of extra information. And then obviously these unique superpowers that thermal imaging devices have, they have some military applications, one or two. And so thermal imagery is a really important development on the military sector. Obviously you have things like heat-seeking missiles that need the capability to find heat sources in the sky and home in on those, but obviously various targeting devices for vehicles, the ability to look for the engine cores of other vehicles that you are hunting on the battlefield. Super helpful. And then drones carrying thermal imaging through the air so that you can look down and actually see where warm people are trying to hide beneath camouflage netting. That's kind of a game changer. And weapon sights, once these things are small enough and durable enough that you can put them onto actual small arms, that opens up a whole world of possibilities. And that's kind of where we are now. There's a tremendous amount of small, man-portable thermal imaging devices being given to individual guys because there are a million different use cases for the ability to see heat. And I'm not going to go into a ton of those because lots of them are really, really obvious. And figuring out what your actual mission requirements are is very important to figure out which use cases you're looking for in a thermal imager, because the devices are different, but also because, as I said before, the way that thermal radiation works is very, very different than the way that visible light works. It has fantastic magical abilities to see through things like smoke and fog and some foliage, but then again, it also cannot see through clear glass. So understanding how this works is going to help you figure out what you can actually do with it. And so let's try to break down that a little bit now. If you're like me, you have spent your entire life operating in the visible light realm, with, a few exceptions where you messed around with night vision or some thermal devices. You are used to using your brain to figure out what's going on in the spatial world by reflected values for the most part. When you look around, you see visible photons being bounced off of something from a light source. And your brain is really good at figuring out, based on shadows and shading and stuff like that, what the three-dimensional shapes of things are, what they're made of, simply by looking at that reflectance data, whether something is shiny, whether something is soft. Oh, by the way, I should mention we're recording this podcast while James and I are going on a hike. So if the audio quality is bad, we'll re-record it. If the audio quality is okay, sorry. If the audio quality is good, then we'll probably keep doing this because it's a good way to make the most of the time. But we're walking around outside right now, and all the light that we can see with our eyes is essentially coming from a single source, the sun. And that helps us to really understand the world around us because our brains are really well trained for that. When you put on night vision goggles, Same thing, you can see a little bit further into the infrared spectrum, but all those infrared photons still acting just like visible light photons, physically speaking. And even in that shortwave IR space, that really, really long form IR space where very, very few sensors can actually see, still acts a lot like visible photons. And there's some advantages to being able to see into the space. For example, the ionosphere actually glows at night and emits a ton of shortwave infrared photons, like 5 to 10 times as much as regular starlight. So having the ability to see into that range is cool because there's a whole bunch of extra light in that particular wavelength that other people can't see because SWIR-capable sensors are kind of rare. But once you go beyond that and you're in the thermal range, everything changes. In this thermal dimension, everything is emitting its own photons, so to speak, instead of reflecting them from a single source. So, for example, let's talk about a bar of iron. As you probably know, a bar of iron does not emit a whole lot of light unless you heat it up really, really hot. So, once you get a bar of iron to about 2,000 degrees Fahrenheit, it is white hot. And we say that because it's actually emitting white light. It's emitting the entire spectrum: red, orange, yellow, green, blue, indigo, violet. I think that's correct. So you see white light coming off of that bar of super hot iron. And then as the iron begins to cool, you get a little bit less light. You see fewer visible photons coming off of it, but you also see a smaller amount of the spectrum all the time. So as it cools to like 1800 degrees Fahrenheit, it now is just yellow. 1600, it's orange. It's pretty much kicking off that 600 nanometer wavelength of light. 1200 is a bright red light. Now 800 degrees Fahrenheit, you get this dim red light. We're right on the edge of infrared, but there's still a fair amount of visible photons being emitted by this hot bar of iron. Once the bar of iron gets down to like 400 degrees Fahrenheit, it's still pretty hot, but it is no longer emitting visible light, but it is emitting infrared light, probably around the 900 nanometer space. And if you had your night vision goggles on, you would be able to see this iron glowing, even though it doesn't glow in the visible space. Now, quick side note, different metals emit different wavelengths of light at different temperatures, which is interesting from a suppressor standpoint. So titanium suppressors actually start emitting infrared light at lower temperatures than certain other metals, which is a really useful thing to know if you are out on the range with a titanium can and people are looking at you with night vision. They're going to see suppressor glow way, way earlier than guys without night vision. But back to the iron bar. Once the iron bar cools down to, say, 50 degrees Fahrenheit, it is no longer emitting any visible light, obviously, or any light that you can see with your night vision goggles. But it is emitting thermal energy that you can see through your thermal imager. So if that 50-degree iron bar is sitting on a surface that is, say, 40 degrees, you will see that it is glowing hotter than what it is sitting on. Or if it's sitting on a warmer surface, then you will see it colder and standing out based on the thermal energy that is coming from whatever's behind it. You can think of the thermal world as a place where light doesn't bounce off of things and have shadows, but as a world where everything is painted with glow-in-the-dark paint and everything is glowing with just slightly different amounts of radiance. That is your only way to differentiate between objects. And obviously I'm simplifying this a little bit because even within the thermal space there is in fact reflectance and absorption and emissive qualities that differ from material to material, but you kind of get the idea. It is just a whole different world, and materials are going to react differently and behave differently than you expect. Again, like glass, which is completely transparent to visible photons and completely opaque to thermal energy. And there's a bunch of types of plastic where the opposite is true. So I think it's important to have a rough understanding of this before you go out and spend, I don't know, $4,000, $6,000, $8,000, $10,000 on a thermal imaging device. Figure out what it is that your use case actually is, what your mission requires, and what it is that you actually are going to need to accomplish that. The good news is that you can start doing some of that research right now without spending any money. What you need to do is start watching videos recorded through different thermal devices, drones, weapon sights, all sorts of thermal imaging captures are up on YouTube and Instagram for you to look at. And as you look at them, look at the different materials that are in the scene and the way that that thermal camera interprets them, and the way that your brain has to work to reinterpret them back into what they are. So, for example, if you watch pig hunting videos, you will often notice that in the background, the vegetation is all the same color, or technically it's not the same color, it's the same value. And that is really, really good when you are trying to locate a target that is not made of foliage. Amongst foliage, that's going to stand out. But on the other hand, if you are trying to navigate through dense forestry, maybe the ability to differentiate between twigs and shrubs and bushes and branches that are right in front of you is a little bit more helpful. And again, this kind of changes when the circumstances changes. So if you watch videos where guys are hunting in the snow, obviously there is a tremendous temperature differential between that cold snow and that, 96-degree pig that they are looking for. When it's 96 degrees outside, that window changes a little. And most devices kind of auto-expose between the hottest and the coldest thing that are in the scene, but it really depends on the sensitivity that the sensor can handle, whether it can look for objects that are 1 degree or half a degree apart in thermal space. And sometimes you don't need extreme sensitivity in a military scenario. You actually want the opposite. You want extreme dynamic range, because you are looking for a 98.6 degree human who is standing right next to an 8,000 degree fireball that you just caused with an explosive. And you need a device that can handle that kind of spread. So as you watch videos from different thermal sources, these are some of the things you should be looking out for and really thinking about what you actually need in terms of dynamic range, in terms of sensitivity, and also in terms of resolution. Obviously, the higher the resolution, the more detail you have to work with. And if you are only doing target location, maybe you don't need so much. And what is the range that you need to actually be seeing stuff at? Target identification, on the other hand, is a little trickier. I've heard at least one verifiable sad story of some guys who were out pig hunting with thermal weapon sights, and they saw a pig-shaped blob that was at roughly pig temperature, and they fired into it only to discover that it was one of their hunting party crouched down behind a bush. And positive target identification can be really tricky with thermal devices. One of the ways that we identify individual people, for example, is the three-dimensional shape of their face, which we identify through shading that comes from light sources. And when you look at people through thermal imaging devices, you only see the shape of their face as defined by, their vascular system mostly, and how much fat they have in their cheeks and stuff like that. So it's actually really difficult to identify people positively through thermal scopes, and you should take all of this stuff into account based on your mission criteria. Another really important differentiator of devices when it comes to price and availability, on top of resolution and sensitivity and dynamic range, is refresh rate. So if you're planning on running around and shooting at pigs that are running at high speed, you're going to need a really high refresh rate. You're going to want a thermal scope that has 30 or 60 frames per second of that thermal feed. But a device that has a much lower refresh rate, something more like 15 or 10 or even 9 or 8 frames per second, still would have some value as a detection tool, as a diagnostic tool, as a sentry tool. And the difference between a 60 hertz device and a 12 hertz device is a huge amount of money. So again, your mission needs to dictate what your requirements are, because that's going to have a massive, massive impact on what it is that you can actually find available and afford. So hopefully this really simple overview on the difference between visible photons, near infrared photons, far infrared heat data helps you have a little bit better idea of what's going on and makes it a little bit easier for you to do the research. And again, start watching videos from different thermal devices and start to really look at what you can see in the sky, on the ground, different types of vegetation, sparseness of vegetation, what things look like in the summer, what things look like in the winter. And hopefully this gives you a little bit better idea of where to start and what to look for, and you can learn more about this space, because it is fascinating, and as Grand Thumb said, yeah, it's it's pretty important. I think we're seeing what a massive game changer this is in Ukraine, so yeah, be aware of how much the game has already changed and what it is changed to. We are certainly doing a lot more thermal research this year than we have in previous years. Stuff with weapon-mounted devices, helmet-mounted devices, drone-mounted devices, and we need to produce some more content on that, specifically video content, because that is where this stuff should actually be shown. Of all the things we've talked about on this podcast, this is probably the most visual, probably the one that would have benefited the most from examples. So we will be working on that. And in the meantime, keep listening to the podcast. Keep rating it 5 stars on Spotify if they will let you, and go watch some pig hunting videos and see what you learn.